Katie Hall is the Chief Technology Officer of Witricity, which is a wireless transmission company that is a startup and will soon, I gather, have commercial products ready.
Good morning. Thank you very much for that nice introduction, Steve. And I'd like to start by thanking the IEEE for inviting me to be here today. This is a great event, and it's truly an honor and a pleasure to be here, so I appreciate the invitation very much. So my name is Katie Hall. I'm the Chief Technology Officer at a startup company called Witricity. And what I'm going to talk about today is to give you sort of a story about the origin of the idea behind the technology that we're developing. I'm going to tell you about some of the existing technologies that are out there and why we had to come up with a new capability. I'll tell you a little bit about our company and what we're working on now, and then finally I'll summarize. So the idea came from Professor Marin Soljacic, who's a professor in the physics department at MIT, and he'd been awakened in the middle of the night for probably the 5th or 6th time that month by his cell phone beeping because it needed to be recharged. And he had a cell phone that had a kind of a quirky characteristic in that you couldn't just turn it off when it started beeping like that. You actually had to plug it in order to recharge it. So not only were you awakened in the middle of the night, but now you had to find the cord. And he says he remembers standing in his kitchen and seeing the outlet right on the side of the wall and the cell phone in his hand and thinking, you know, the power is right there. Why can't this cell phone take care of its own recharging? And so he started to really think about that, and he was looking around at, had other people thought of this and what kind of work had been done. And of course, he looked back to some of the very early inventors of electricity who had actually envisioned that power might be transmitted wirelessly, even over very long distances. But I think it's probably because they never imagined that we would fill our planet with copper wires in order to carry the power from where it's generated to where it's consumed. So then he said, well, all right, this is a different problem. I don't need to transmit it over long distances. I already have power coming into my house to this outlet right here. How do I get the power from the wall plug to the device? And so again, you know, looking at some of the technologies that were available at the time, he looked at some radiative schemes. And one example is an omnidirectional radiator. In this case, think about it like it's a radio tower or television broadcast tower. And it's sending information. It's typically used for information, sending out information in all directions. And this is indeed a kind of wireless energy transfer, but it's very inefficient. Only a very small amount of power actually makes it to where a device needs to use it. The rest of it is radiated into space. So you can think about directed radiation schemes. For example, lasers is one example. And here what you're going to do now is confine and direct the energy towards the device that you're trying to power. And this actually can transmit power efficiently over distance, but it has a couple of drawbacks. The first being that you have to have typically an uninterrupted line of sight between the transmitter and the receiver. Another thing is if either of those are moving around, you need some kind of tracking and steering mechanism in order to keep those things aligned. And if the power levels are medium or high level, it may actually be dangerous to get in between the transmitter and the receiver. So another scheme that people have used is induction, and this is very well known. It's probably the most common example that people use to describe this as a transformer. And in a transformer, you have two coils that are very close to each other, but they don't touch. So in fact, they do transfer power wirelessly from one coil to the other. But with a transformer, if you start to pull those coils apart, the efficiency of the transfer drops off significantly. And still, there are commercial products that are available today that are based on this technology. If any of you have an electric toothbrush that's rechargeable, in this case, the nice thing about the induction is that you don't have to have any exposed electrical contacts, which might be nice in an environment where there's water, for example. And we're now seeing companies that are starting to make these mats, or they're sometimes called charging pads, which plug into the wall and in some ways serve as the source. You can think of those as one of the coils in the transformer, with the second one being built into a device, like a cell phone example is shown in this picture. And here you can again have wireless power transfer, so by just placing the phone on the mat, you can indeed charge it. But these kinds of techniques are referred to as proximity chargers because you need to have the device that needs the power and the source of the power be very close together. So these don't solve that problem that Marin was thinking about. How do I get the power from the plug to the device? So he kept thinking about it, and he found himself naturally thinking about resonance. Resonance is something that occurs in a variety of systems in nature, and in particular, he was thinking about a way to exchange energy using resonance. And coupled resonators are a very attractive way to think about exchanging power because they have this very interesting and attractive feature, which is that two same frequency resonant objects will exchange energy between themselves very efficiently, but they're very inefficient at giving energy to anything else, any kind of off-resonant or extraneous object. And so Marin really started to think about magnetic resonances. And I'm showing here a cartoon of a very simple kind of a magnetic resonator, which is based on a loop of wire and a capacitor, an inductor and a capacitor. And if you apply a current to this loop, you'll generate a magnetic field and an electric field. And the energy goes back and forth between these two fields is what makes it a resonator. But if you notice in the vicinity of the coil, the field is primarily magnetic. And this is particularly attractive for power transfer applications because magnetic fields are safe for biological organisms. They're very weakly interacting with not just humans and tissues, but also things like wood and brick, common building materials. So as we think about this technology going forward, we think about building these kind of devices into houses behind walls or under floors, for example. If you bring a second resonator into the vicinity of this first one, what happens is that the magnetic field from the first resonator will induce a current in the second resonator, and that can be used now to power a device or to recharge a battery, for example. And even with this very simple structure, the modeling that the team performed at MIT showed or suggested that this could be very efficient even over distances that were relatively large. Actually, we refer to them as mid-range distances, distances of a few meters within a room, let's say, or thinking about, again, going from the plug to the cell phone. So these kinds of resonances should be very efficient at transferring the power, but as they say, seeing is believing. And so it was really this experimental demonstration at MIT, I think, that raised people's interest. This is a picture of the team at MIT sitting between two electromagnetic resonators that they constructed in order to show how the technology worked. So in this case, the electromagnetic resonator are those copper coils that you see. And the coil on the left is the source coil. The coil on the right is the device. And you'll see that there's a light bulb here attached to the second coil, and it's actually being powered. 60 watts of power is being transferred to that bulb. You'll notice that the team is sitting directly between the two coils, and that they're not interacting, they're not affecting the energy transfer at all. And again, this is because this is a magnetic field that's being used to transfer the energy. And most materials just look like free space to the magnetic field, so the system works just fine. In this particular case, the power was transmitted over 2 meters. The size of the coils was about 60 centimeters, so in fact they did show power transfer over mid-range distances, and again, the beginnings of the technology that Marin had been thinking about for some time. And when this paper was published and this photo went out, I think it really captured people's imaginations, and a number of people, well, just a great number of people got very excited and started to send emails to Marin and his team asking questions about what the technology might be used for. You know, how can we envision it? And a lot of people asked about what was really the motivating factor for Marin. You know, can I use this technology to power portable electronics or home electronics, things like a TV, a cell phone, or how about recharging my game controller? We've had a lot of questions about industrial applications. People talk a lot about these robot arms, for example, that are always moving but have a power cord that run up through the center of those arms to supply power. And after some number of uses, the copper breaks down. And that's a common failure mechanism in assembly plants, for example. Things like slip rings. In some ways, we like to think about the technology potentially as a wireless connector, as a way to get across platforms in order to supply the power. Some of the applications we've been asked about are medical. This is a picture of an implanted heart device. In a lot of cases, some of the technologies that people are looking to use in the medical arena require a fair amount of power. They may have batteries that have to be replaced surgically every couple of years, or they may not even have enough power to be able to run. And so we really believe that the technology has some potential there in order to enable new applications. You hear a lot about smart cards, I think. People are talking about them. Well, the smart cards are getting smarter and smarter, and when that happens, they typically require more power. They've got more computing that's being built onto the chips. In some cases, they have displays that are being built onto them, and so they require more power, and this, again, is another kind of a potential application. And then finally, I can't possibly tell you about all of the applications that people have thought of when they come to us in a 10-minute talk, and never mind on a 1-minute slide, but I try to just give you a flavor here. So one of the high-power applications that people are asking about is recharging electric vehicles. So we're hearing a lot about the coming of the plug-in hybrid. And it turns out, people really aren't so excited about the plug-in piece of it. It's really that they just would like to have an electric vehicle. And what we envision is that there will be a mat that sits on the floor of your garage, and as you drive in, the car will start to recharge itself. So anyway, based on the great interest and realizing that there was engineering to be done to take this technology and try to build it into commercial applications, Marin and his crew at MIT co-founded a company called Witricity Corporation. We're located in Watertown, Massachusetts. We were formed in November of 2007, and we're the exclusive licensee of the MIT technology. And we're really trying to develop this technology with the plan to deliver power over distance. And by distance, I mean anywhere from centimeters to several meters. And power levels can be milliwatts, like the smart card that I showed you in the last slide, all the way up to kilowatts, which is the power that it takes to recharge an electric car. And just to give you a sense of some of the progress that we've made, I want to show you a demonstration that we have running in our offices in Watertown. This is a commercial off-the-shelf television that we bought. It's actually a combination television DVD player. And in this particular case, what we've done is to integrate the device coil into the base of the TV. And you can see now that the camera is panning all around so that you can see there are no wires going to this television. There's no batteries here. The source for this particular demonstration is actually built into the frame of that picture, so it's sitting behind the picture. And what's going to happen now is if we apply power to that source coil, it's going to create the magnetic field I told you about. That magnetic field will be picked up by the device coil that's in the TV, and the TV will turn on. And in this case, we're directly powering it now, so this is transferring about 50 watts of power to play the TV. And again, you see here no wires and no batteries. So this is showing you that the technology can be integrated into the devices that it's meant to power. And again, you know, hopefully you see the wide range of potential applications. So in summary, you know, our vision is of a world where this Witricity technology is as commonplace as batteries and extension cords are today. I talked about a couple of the applications, but we think there are just a variety in the home, office, and workplace. I told you about improving, you know, people's lives with some medical applications. And we do believe that there's a great chance that this can accelerate the adoption of green technologies because it's going to make a lot of these newer technologies more reliable, more convenient, more accessible. So our mission is to build a successful company to deliver this technology worldwide, and we're excited because we imagine that there must be incredible applications out there that we haven't even imagined yet. So thank you very much for your attention.